Welcome back everyone. In this lecture we will define a base of a root system and prove its existence. So, later we will see that if we take the set of all bases on this set the while group naturally acts semi simply and transitively. So, let us first see some examples, later we will actually see the definition of base. For example, let us recall what is the root system B2. So, if you recall the root system B2, so this is going to be the set of all. So, if we fix this alpha beta such that beta of alpha. So, if we fix this beta alpha, this Cartan number to be minus 3. So, this is the Cartan number. Sorry, this is we fix it to be minus 2. So, that means the absolute value of this Cartan number beta alpha, this is max actually, that is exactly 2 in this root system B2. So, that is how we are choosing this alpha beta. So, then we saw that this root system B2 it is going to consisting of the following roots plus or minus alpha, plus or minus beta, plus or minus alpha plus beta, and then plus or minus beta plus 2 alpha. So, in particularly these roots alpha and beta, so they are some special roots inside B2 and then they actually kind of divides this B2 into 2 sets. So, one is B2 plus which is consisting of alpha, beta, alpha plus beta and alpha beta plus 2 alpha. Okay. So, this is somewhat gives the roots that are like behaves like positive roots with respect to these alpha beta. So, what I mean by positive roots, so they are non-negative integral linear combination of this alpha beta. Okay. So, this is actually subset of Z plus span of this alpha beta, where Z plus actually all the non-negative integers. Okay. So, in particularly this B2 becomes disjoint union of this B2 plus and then minus B2 plus. Okay. So, this actually tells us that we have some special subset of this B2 and all the elements of this B2 are either non-negative integral linear combination of these elements alpha beta or non-positive integral linear combination of these elements of beta. So, such a subset we call it as base. Okay. So, this is in some sense the definition of base. So, this is actually very clear that all these rank 2 root systems they have bases. So, I will encourage you to identify base for other root systems which is A2 and G2 and so on. Okay. So, now so we are ready to define what is base. Okay. So, this is actually motivated from the earlier example, that is what we seen B2. So, we fix a root system, let us call it phi. So, this is a root system. So, this is let us say sitting inside this Euclidean space E. So, then you want to call a subset let us call it pi. So, this is a subset of phi. So, it is called a base if the following conditions satisfied. So, what are all the conditions? The very first condition we call it the base 1 condition. So, this pi must be a basis of this E. So, this is a basis of capital E. In particular, all the elements of this roots phi that must be written as some linear combination of elements from pi. But you can see that we have some very strong condition than just being linear combination. So, that is what we demand it as condition 2. So, if we take any root, so each root beta of phi, so that can be written as either non-negative integral linear combination of elements from phi or non-positive integral linear combination of elements from phi. So, each root beta, So, we should have beta either is inside z plus span of pi or beta is in minus z plus span of pi. Okay. So, what is the meaning of that in terms of, let us write it in terms of coefficient. So, beta can be written as summation, let us say k alpha, alpha coming from this pi. So, now what we should have, so this is guaranteed from B1. So, B1 tells that each element of this beta, each element beta of phi, that must be written as some linear combination of elements from pi. So, what the condition B2 demands, so B2 gives that either this k alphas, they are all non-negative integers for all alpha in pi, or these k alphas are all non-positive integers for all alpha in pi. So, this is the condition that we get. So, this is some very strong condition on the coefficients, but we can see that using this rank 2 root systems. So, base exists for all rank 2 root system, okay, by giving this explicit description of rank 2 root system. So, this is something we will prove it for general root system. So, that is our main theorem in this lecture. For that purpose we need to actually develop some language, but before that let us actually use this base and then define some important terminologies. So, what is that? So, let us say once you have a basis, okay, once you have base, this base let us say which is subset of pi, okay, this is base. So, then all these elements of pi, so they are called simple roots. So, elements of pi, they are called what is called simple roots. So, that means all other roots are built from these simple roots, okay, because all other root from condition B2 you can see that either it is non-negative integral linear combination of simple roots or non-positive linear combination of simple roots. Of course, elements of phi are called roots, okay. So, that is what suggests this simple roots definition. So, now you can also define what is called positive roots and negative roots with respect to all these coefficients being either non-negative or non-positive, okay, that is also well motivated. So, what is this positive roots? So, positive roots, so that is by definition. So, you take beta inside phi and then write beta equal to summation k alpha alpha, where alpha coming from pi. So, you call beta is positive, is said to be positive root or in symbolic positive root if all these k alphas, they are all non-negative integers for all alpha in pi. Okay. So, similarly one can define negative roots. So, for negative roots, so you take this k alpha being, okay. So, respectively, so here being negative, you take k alphas are all non-positive integers for all alpha in pi. So, this is how you can define negative roots and positive roots. So, then by condition B2, so what we get? So, we can define this beta plus or minus. So, this is being the set of all either positive or negative roots. So, this is the set of all positive respectively the negative roots. So, then from B2 it is clear that capital phi can be written as disjoint union of capital phi plus and phi minus, and phi plus is actually just negative of phi minus, or phi minus is just negative of phi plus. Okay. So, these things are immediate. So, now we also use the symbolic notation to denote positive roots. So, basically we are going to define a partial order on capital E. So, that actually kind of suggests this symbolic notation. So, what we want to do? We want to define this partial order, which we call it greater than or equal to. So, this is partial order that we want to define on capital E using the base pi. So, how one defines this? So, you say that lambda is mu, the both are let us say elements of E, for then lambda is bigger than mu if and only if you subtract mu from lambda. So, then this must be a sum of positive roots. So, that is how you define this lambda greater than mu. So, this is a sum of positive roots. So, from earlier observation you can see that this is if and only if lambda minus mu is inside this z plus span of this capital pi. So, that is how you define this partial order. Okay. So, I will leave it to you to check this is actually a partial order. So, then in from this definition you can see that your root is positive, your root is positive. So, let us say a root beta is positive if only if this beta is greater than 0. Okay. So, this partial order it's in a way suggests that how to define these positive roots and negative roots. So, now we will make one simple observation about the elements of this base, and then we will actually move ahead and then prove existence of base. So, right now like from this definition it is not very clear whether base exists or not. So, since we know that the span of phi is capital E, so some basis of capital E is sitting inside phi, that much only we know, but there is no guarantee that we have a base, because base consisting of this second axiom. So, that axiom demands that you can actually write any root beta in phi as beta as either non-negative linear combination of this elements of pi or non-positive integral linear combination of elements of pi. So, this is very strong condition. Okay. So, that condition actually is somewhat very demanding. So, we need to actually kind of check this second condition if we want to prove existence of base. Okay. So, let us see what we get if we have base. Let us start with the base. So, let us say pi being a base. So, then we can actually observe that if we take two elements inside the base, let us say alpha beta. So, they are elements inside base such that beta is not equal to alpha. So, both are these elements. So, in this case we can claim that this beta minus alpha is never a root. So, beta minus alpha is never a root. So, that means alpha minus beta is also a never root by symmetric. Okay. So, how one proves this? So, for this purpose we need to understand what happens if we take the inner product between alpha beta. Okay. Let's assume that inner product alpha beta is actually positive. So, then since alpha is not equal to beta, so if alpha beta is positive, since alpha not equal to beta and pi is a basis. So, that implies this beta is not equal to plus or minus alpha. So, this is something we already have. So, then using this earlier lemma that we proved, so whenever you have the inner product is positive, then that immediately implies that this alpha minus beta or beta minus alpha, that is a root. So, then using our earlier result we can see that this beta minus alpha is a root. But then immediately you can see that this beta minus alpha, this has mixed sign coefficients. Okay. This is a root, let us call it gamma. So, this gamma is written as linear combination of elements from pi, but whatever the coefficient, that linear combination that we are getting, that must be unique expression, but this has mixed sign plus and minus. Okay. That is not the case. So, this violates B2. So, this violates B2. So, that means we cannot have the inner product positive. So, that immediately implies the inner product beta alpha must be non-positive, and that also immediately implies that this beta minus alpha is not a root, okay, and beta minus alpha is not a root. So, what this says, this puts lots of geometric constraint on the elements of the base. Okay. If we take something is a base, then all the elements of this base must be, the angle between them must be obtuse, that is what it says. Okay. So, now let us develop something and then try to prove the existence of base. So, for that purpose we need to understand what happens if we take geometrically the union of all the hyperplanes that are perpendicular to, that are defined by elements of this phi. Okay. So, recall, so we have this root system phi. Okay. So, this is a root system, and root system by definition this is a finite subset of capital E. Okay. This is finite. So, once we define this root system, there are some important objects that are associated with this root system. So, for example, given alpha, so we have this hyperplane which we called it P alpha. So, that is perpendicular to alpha. So, what is this P alpha? This is those x in E that is perpendicular to alpha. So, this is the hyperplane. So, that means the dimension of this hyperplane is just 1 less than the dimension of E. So, this is the hyperplane, and we also have a reflection S alpha in W. So, this is just defined from E to E. So, that reflects this this is just a reflection with respect to the hyperplane P alpha. So, more algebraically, so this is given by S alpha of lambda equal to lambda minus twice lambda alpha divided by alpha alpha alpha. So, this is how it is defined for all lambda inside your capital E. Okay. So, now let us look at these hyperplanes which are actually perpendicular to these roots alpha. So, then you can see that these hyperplanes, so how many are there? There are only finitely many hyperplanes are there. So, if you take this P alpha, alpha coming from this phi. So, note that up to this modulo this plus or minus. So, we can take this modulo plus or minus, because P alpha will be same as P minus alpha. So, anyway you take this union of this P alpha, you can see that this is a closed subset of capital E, okay, and this is just union of hyperplanes. So, these hyperplanes, okay, so now this cannot cover entire E, because for example, one can immediately give measure theory proof. If you take a measure that is defined on this Euclidean space which has dimension, let us say L, okay, let us say dimension of E equal to L. So, then E is naturally isomorphic to R power L. So, if you take that standard measure on capital E, then you can see that the measure of this union of this P alpha, that will be 0, because each hyperplane will have measure 0, and this union of finitely many hyperplanes will have definitely measure 0. So, that proves that the complement of this hyperplanes, okay, union of hyperplanes, that must be non-empty. So, you take this E minus union of P alpha, alpha in phi. So, this is a non-empty subset of E. Not only that, this is naturally a open set. So, this is a open subset of E, as union of P alpha is a closed set. So, if you think about it, since we have removed only the finitely many hyperplanes, so you can easily see that this is indeed actually a finite union of connected subsets of capital E. So, this can be written as so every time you actually remove one hyperplane, then what happens? So, that divides E into two parts. Okay. Let us say you are inside this R2. So, if you take this plane, that is the line passing through origin. So, if you just remove this line, so then you get two distinct components of the complement. Okay. So, now if you remove hyperplanes that corresponds to this phi, then by induction you can see that. So, there are exactly the cardinality of phi number of connected components are there for this E difference union P alpha alpha and phi. So, there are cardinality of phi number of connected components of this E difference union P alpha alpha and phi. So, this is something you can just use induction and prove. So, use induction and check this. Okay, this is something trivial. So, then that proves that this complement of this union P alpha alpha and phi, it is a open set which has this many number of connected components, and each connected component will be actually open subset again, and that is more than actually open, it will be a convex subset. So, that is something I will leave it to you to check. Okay. So, if we take this E difference union of P alpha, so then a connected component of that, a connected component of this E difference union P alpha alpha in phi, so is indeed a convex open subset, a convex open subset of capital E. Again, this is also you can use induction and prove, because if you remove one hyperplane, it is easy to see the complement is indeed actually has two components and both are convex open subsets. And then if you keep removing, then you can use induction and then see that the component that we will be keep getting is will be convex and open subsets. And these connected components, they will be called Weil chambers. Okay. So, these connected components of, so this is the definition, connected components of E difference union P alpha alpha and P are called the Weil chambers. Of capital E. Of course, we can take this set of Weil chambers and then we can see that this Weil group will naturally act on that. Okay. Before actually looking at this Weil group action, let us make some remarks about these Weil chambers. So, the elements of this E difference union P alpha, that will be called regular elements. Okay. An element of E is called regular, if this gamma, let us say an element gamma of E is called regular, this gamma lies inside this E difference union P alpha alpha in phi. Otherwise, it will be called singular. Okay. Otherwise, it is called singular. So, that means it is orthogonal to some alpha for alpha in phi. Okay. So, this is again a definition. So, if we take a regular element, then the regular element will lie inside some connected component, that means it will lie inside one Weil chamber. Okay. So, that actually kind of uniquely picks up that Weil chamber. So, given regular element, okay, so given gamma inside E which is regular, you can see that this gamma lies inside one connected component of E difference union P alpha alpha and phi. So, this is defined inside in unique connected component of E difference union P alpha alpha and phi, and that unique connected component we denote it by C gamma. So, this is that Weil chamber, okay, the Weil chamber. So, that contains this gamma. So, that is what we denoted by C gamma. So, now what we can see, so if we take this gamma that is regular, okay, and then you take some other gamma dash, so that is also regular, okay. So, so here is the observation, gamma, gamma dash both are in E, so both are let us say regular elements, okay. So, then assume that both of them lie on the same side of each hyperplane P alpha alpha and phi, okay. So, assume that gamma gamma dash, so they lie on the same side of each hyperplane P alpha where alpha in phi. Okay. So, then that means you can see that, so this C gamma dash, so that must be same, okay, because they all lie inside same side of the hyperplane, and then you can construct this subset of phi, so which is defined using this gamma, okay. So, maybe let me just tell me about that, let me just tell about that. So, you have this gamma gamma dash, so that is lying on the one side of the like hyperplane. So, then this implies immediately that C gamma is same as C gamma dash, okay. So, this is the immediate observation. But before that let's actually like see what one can do with this regular element, okay. So, let us start with a regular element, let us say gamma in E which is regular. So, then naturally gamma is not lying inside this union of P alpha alpha in phi. So, that implies gamma alpha, the inner product, so that is going to be non-zero for all alpha in phi. So, now note that if gamma alpha is positive, okay, so then if and only if gamma of minus alpha will be negative, okay. So, this is just a simple observation. So, this is something motivates us to define what is called this phi plus of gamma. What is phi plus of gamma? So, this is those betas inside phi such that beta alpha is actually positive, okay. So, beta alpha is positive. So, in some sense we will prove, so this will actually play a role of what is called this set of positive roots, okay. So, in particularly we will be able to find a base inside this phi plus of gamma. So, what this is actually those roots, so sorry, those roots that lie on the one side of this hyperplane P gamma. So, this given gamma inside E, so you have this hyperplane B gamma, so which is those x in E such that which is perpendicular to this gamma. So, pictorially, so you have this hyperplane, so that is actually just somewhere. So, then you can see that you are collecting roots beta. So, that is let us say if this is gamma 0 and then let us say this is gamma positive. So, then you are collecting roots that are lying on the positive side of this hyperplane, and of course, the hyperplane divides capital E, okay, or the E difference P gamma will be two components, one is the positive component and one is the negative component, and we are collecting roots that are lying in the positive component. So, what is our claim now? So, we can see that this phi plus gamma contains actually a base. So, how do we get that base? So, that to get that base we can actually go back to the definition of base and then see what base demands. So, basically what base demands, so base must be a basis and each element of a root system must be either non-negative integral linear combination or non-positive integral linear combination. So, that motivates us to define what is called this indecomposable elements phi plus gamma. Okay, let us call that is delta of gamma or let us call it pi of gamma. Okay, what is pi of gamma? So, pi of gamma is a subset of phi plus of gamma. Okay, what it is? It is just those elements of phi plus gamma that cannot be written as sum of again elements from p plus of gamma. So, that is those beta in phi plus gamma such that beta is what is called indecomposable. Okay. So, for that what we need to define what is called decomposable. An element beta of phi plus gamma is said to be decomposable if beta can be written as beta 1 plus beta 2 for some beta 1 beta 2 inside your phi plus of gamma. Okay. If a given element cannot be written as sum of two elements from phi plus of gamma, then you call that is indecomposable. Then you collect all this beta inside this phi plus gamma which is indecomposable. Since this phi plus gamma is a subset of phi and phi itself is finite, so that forces that phi plus gamma to be finite. So, then since it is finite set, we will have indecomposable elements, because using some standard argument you can see it must have indecomposable elements. Okay. So, now you take all these indecomposable elements in phi plus gamma. So, what is our claim? So, this will be a base. Okay. This is our claim. This pi of gamma is indeed a base of phi. So, for that purpose we need to actually prove two things. One is this pi of gamma must be a basis, and second thing is each element of phi can be written as either non-negative linear combination or integral linear combination of elements from pi of gamma or non-positive integral linear combination of elements of pi of gamma. So, we will prove both of them in one go. So, how one can prove this? Let us see. So, first of all you can see that each root in phi plus of gamma must be non-negative Z linear, actually non-negative integral linear combination of elements of pi of gamma. So, why that is true? So, this is here is the claim, this is the first claim. Each root inside this phi plus of gamma is a non-negative integral linear combination of this pi of gamma. So, why this is true? So, where one can induct on this gamma comma alpha. So, let us start with alpha in phi plus of gamma. If of course alpha is in pi of gamma, then we are done. So, assume that alpha is not in pi of gamma. So, then alpha is not indecomposable. So, that means alpha is decomposable. Okay. So, you can write alpha as some beta 1 plus beta 2, where beta 1 beta 2 both come from this phi plus of gamma. So, now note that if you take the inner product gamma alpha, so then that must be equal to gamma beta 1 plus gamma beta 2. Since gamma alpha, gamma beta 1, gamma beta 2 all of them are positive, then that implies gamma of beta 1 is smaller than gamma of alpha and gamma of beta 2 again smaller than gamma alpha. So, now by induction, okay, in some sense you can call this is height, okay, the height is just gamma alpha. It may not be some integer or anything, but it is some quantity that measures something related to alpha. Okay, that quantity is actually kind of goes down for beta 1 and beta 2. So, then that says using induction you can see that beta 1 and beta 2 can be written as, so using induction both beta 1 beta 2 can be written as non-negative integral linear combination of elements of pi of gamma, and that implies immediately that beta 1 beta 2 also can be written, which is alpha. So, this proves that any element of alpha can be written as non-negative Z linear combination of elements of pi of gamma. So, now note that it is easy to see pi is actually equal to pi plus of gamma disjoint union minus pi plus of gamma. So, that is because if gamma alpha is positive, if and only if gamma of minus alpha is negative. So, using this you can see that any element of pi can be written as either Z non-negative Z linear combination of elements of pi of gamma or non-negative non-positive Z linear combination of elements of gamma. So, that proves B 2 is satisfied. So, B 2 is satisfied. So, we need to check the B 1, that is the elements of pi of gamma that must be linearly independent. So, let us check that. So, why elements of pi of gamma is linearly independent? So, that is because one can check it is geometrically constrained. Okay. Here is the second claim. So, if we take alpha beta, so that is coming from pi of gamma, then one can immediately prove that this the inner product alpha beta that must be non-positive unless alpha equal to beta. Okay. So, how one proves this? So, suppose if this is not true, okay, if this is not true, then what will happen? Then alpha beta must be positive. So, then that implies using that lemma that we proved in the earlier class, then we can immediately conclude that beta minus alpha must be a root. So, this is must be a root. So, if this is a root, then either beta minus alpha will be inside phi plus of gamma or alpha minus beta will be in phi plus gamma. So, this implies that either alpha minus beta is in phi plus of gamma or beta minus alpha is in phi plus of gamma. But in both cases we will get contradiction as follows. Suppose alpha minus beta is in phi plus of gamma, then you can see that you can write alpha equal to beta plus alpha minus beta. So, that means you could write alpha as combination of two elements that are coming from phi plus of gamma. So, that forces that alpha is not indecomposable. It is not indecomposable. So, which is a contradiction because it must be indecomposable by definition of pi of gamma. So, similarly, if beta minus alpha is in phi plus of gamma, you can see that beta will be written as alpha plus beta minus alpha. Again it contradicts indecomposability of beta. So, in both cases we get contradiction. So, that proves that the inner product beta alpha must be always non-positive for all alpha beta which is in pi of gamma such that beta not equal to alpha. So, this geometric constraint in a way actually guarantees that this pi of gamma must be linearly independent. So, pi of gamma is linearly independent. So, how one proves this? You can see that first of all elements of pi of gamma that lies on the one side of the hyperplane gamma and in the inner product between any two distinct elements of pi of gamma that is non-positive. So, these two conditions actually somewhat forces pi of gamma to be linearly independent. So, let us say how one can prove this. Let us assume on the contrary we have a linear relation. Let us say summation r alpha, alpha is 0, okay, where alpha coming from this pi of gamma, where r alpha is coming from this r. So, now you can see that by separating positive and negative term, we can just write it as epsilon equal to summation some r alpha alpha, where r where sum runs over all alpha inside pi of gamma such that r alpha positive, and then similarly which is same as equal to r beta beta, where beta runs over all pi of gamma such that beta is r beta is negative, okay, or minus r beta. So, note that if this summation r alpha alpha is 0, then we can divide this coefficients r alpha to be positive and negative, then you can write this epsilon to be this. So, now look at this epsilon. So, then what happens if you compute the inner product epsilon epsilon. So, this must be greater than or equal to 0 as epsilon being element of capital E. So, now since beta alpha is always non-positive for all beta not equal to alpha that comes from pi of gamma, you can see that this is going to be equal to summation this term comma this term. So, that actually forces that this is exactly equal to summation r alpha minus r beta alpha beta, where now alpha beta they are coming from two different disjoint sets. So, that means this is going to be at most at most 0. So, that forces that this is less than or equal to 0. So, that forces that this epsilon to be 0. So, that means epsilon must be 0. So, we proved that this summation r alpha alpha, where r alpha positive must be 0, as well as summation minus r beta beta, where r beta less than 0 is also 0. So, now since both these sums are running over elements of pi of gamma, and pi of gamma is actually sits one side of the hyperplane. So, what is the property of pi of gamma? Pi of gamma is subset of this phi plus of gamma. What is phi plus of gamma? This is those beta in phi such that beta gamma is positive. So, that tells you that if we take this element epsilon, then epsilon comma gamma, so which is going to be summation r alpha alpha gamma. So, this is going to be 0 on the one hand, but this alpha gamma these are all positive, okay, these are all positive. So, and this r alpha these are all non-negative or positive, okay, this is running over r alpha positive. So, that gives you contradiction, because we are summing over positive terms such a way that we are getting 0, okay. But that is cannot happen unless this sum is empty, unless this sum is empty. So, that forces that there is no r alpha such that r alpha positive. Similarly, you can conclude there is no r beta such that r beta is negative. So, that means the assumption that we have made summation r alpha alpha is being 0 is actually not true, okay. So, that proves that this pi of gamma must be linearly independent. So, this must be linearly independent. So, that way we actually proved that pi of gamma is indeed a base, is indeed a base of pi, okay. So, indeed we will actually prove that this is the only way to get all the bases, okay. So, let me just quickly recall what we did and then I will stop there. So, what we did, we defined what is called regular elements. So, what is regular element? Regular element is an element that is lying inside the complement of all these p alphas. Take gamma, gamma is actually lying inside E minus union p alpha, alpha in phi. So, then this gamma allows us to divide phi into two sets. So, those roots that are lying on the positive side of p gamma or on the negative side of p gamma. So, that allows us to define what is called this phi plus of gamma. This is those beta in phi such that beta of alpha is positive. So, then it is clear that phi can be written as phi plus of gamma disjoint union phi minus phi plus of gamma. So, now then what we did, we actually looked at some indecomposable elements in phi plus of gamma that we denoted by pi of gamma. Pi of gamma, those elements of phi plus of gamma such that beta is indecomposable. So, that means it cannot be written as sum of elements from phi plus of gamma. So, then we proved that this must be a base, inside your phi. So, this is what we proved. Okay. So, we will prove in the next class that all bases should come this way. Okay. I will stop here and I will continue tomorrow. Thank you.